This is an example of a spin hoop apparatus with 4 hoops connected with 3 spin axes at a 60-degree offset. This is an open system which allows the hoops to spin in an unconstrained fashion. All 4 hoops can be positioned in the same plane and become coplanar, and this will be referred to as the neutral state. The edges of the hoops are colored black and white to indicate its spin position at either 0 degrees or 180 degrees, kind of like a heads and tails on a coin. With 4 hoops, that allows 16 different possible neutral states. However, if the other hoop is fixed, that reduces it down to 8 different neutral state possibilities. The open system can transform to a closed system by adding an additional pivot between the most outer and most inner hoops. A magnetic pivot is used in this case. And now the spin or movement of the hoops are constrained, since now there is a feedback loop between all 4 hoops. The hoops now spin in a synchronous fashion, which I'll describe in more details later. The hoop movement has 3 different modes. There's a split mode, where the middle 2 hoops spin as a pair, while the inner and outer hoops spin as a pair. There's a double mode, where the 2 smaller hoops spin as a pair, while the 2 larger hoops spin as a pair. And there is an expanded mode, where all hoops spin independently. This is the more interesting mode, which I'll describe in more details in the upcoming section. The following diagrams illustrate where each of the pivots are located in the coplanar position. Pivots A1 and A3 become aligned while in a neutral state. However, they operate independently from each other and separate when the hoops leave the neutral state. Pivots A2 and A4 are at a 60-degree offset and are also aligned to each other while in a neutral state. This diagram shows the position of the hoops in the expanded state, and this line diagram shows how the hoops intersect at the 12 vertices of a cube octahedron. This is a close-up view of the hoop movement while in the expanded state. And you can see all the hoops spin with the same period, but the speed of the spin varies for each hoop at different phases of the rotation. If you look very closely, the yellow hoop only spins to 180 degrees of rotation. The energy is transferred between the hoops in a feedback loop. Now I'll use a state diagram to show the neutral state transitions of a closed system. In a closed system, with the outer hoop in a fixed position, the hoops are constrained to 3 of the possible 8 neutral states. In this example, it's neutral state 0, 3, and 6. For the split mode, the hoops move between neutral states 0 and 6 and can loop there indefinitely. But the hoops can change modes, but only while it's in the neutral state. The hoops can change from split mode to double mode, but only during neutral state 0. And once in the double mode, it'll loop between states 0 and 3. Or they could change from split mode to expanded mode, but only during neutral state 6. And once in expanded state, the hoops loop between 3 and 6. I'll demonstrate this in the next video. Now I'll inject some spin energy into the system. Right now the magnetic pivots aren't engaged, so they're unconstrained. And at some point I'll slow it down and we'll get the magnetics are now engaged, and it's in a split mode at this point. Stays there momentarily. Now it'll eventually pass through a neutral state, switches now, and that's the double state. Goes back through the neutral state into the expanded state. It makes one more state change, so it passes through neutral state momentarily into the split mode and then back into expanded mode. Notice vibration of the hoops as the energy is transferred between them. Now I'd like to introduce a different way to implement this apparatus, or geometric machine, from a virtual perspective, or a non-physical means. Let me explain this by starting with a structure for a tetrahedron formed by four intersecting planes. In this illustration, the circular discs represent the four planes. Each pair of planes intersect to form a line, which will be referred to as a hinge. The six hinges form the edges of the tetrahedron. The six hinges and four planes form a very stable, rigid structure. However, if we move each of the planes towards the center of the tetrahedron, its volume reduces to zero, and the four planes now intersect at a single point, and the four circles intersect at the 12 vertices of a cuboctahedron, similar to what we saw with the spin hoop apparatus. The six hinges also align with the vertices of the cuboctahedron. Now, if we deactivate two of the six hinges, something very interesting happens. The four planes are now free to synchronously rotate around the four remaining hinges. And now, if we assume the planes can pass through each other in a virtual nature, then the planes can spin 360 degrees in a similar fashion as the spin hoop apparatus. I can only speculate if this could model any behavior found in nature in a non-physical way, like the interaction between the fields of various forces found in nature, or perhaps they may model the relationship between the dimensions of different space-time continuum that could exist in nature. The hoops can have a spin of +1, -1, +1/2, or -1/2. At the fully expanded position, the angle between each pair of planes at each hinge is approximately 70.53 degrees. The angle between each pair of planes can be any value between 0 and 360 degrees. There is a unique position for each pair of planes where the angle is 90 degrees, and if you know one angle, the other angles can be calculated. There are also several other different arrangements of hoops or planes that use different number of hoops or planes with a different angle offset between the spin axes found during the neutral state. This will be described in more detail in a subsequent video.